Topographic maps and satellite views. Today we're going to interpret topographic maps and satellite views to identify land and erosional features and predict how these features may be reshaped by weathering. So here we're looking at a satellite image at a divergent boundary where we have a continental plate and a continental plate diverging. This is actually a picture of the Great African Rift in Africa. So what we're going to do today is we're going to follow along with a note-taking worksheet, and you're going to fill in the blanks. So if I pull up your assignment for today, you are going to read along with me and fill in the blanks as your notes as we go along. So it's a form of note-taking. The answers to the blanks will be highlighted and underlined as I dictate. So, cartographers are map makers. They use data from aerial photos and remote sensing to create maps of Earth's surface. Satellites orbiting the Earth photograph the surface to provide views of the Earth we normally would not be able to see. So here we're going to look at some satellite images of Earth from NASA, and you can play this on your own to go back and spend a little more time with it. Okay. The photos from satellites correlate to the maps that show the shape and the elevation of a given area. These are called topographic maps. Topographic maps are useful because they model three-dimensional land using lines and symbols. Topographic maps show the location and shape of landforms using contour lines.
Anyone that's been four-wheel driving will have used one of those maps with all those wriggly lines on them. But do we really know what those lines mean? Once you find out what they mean, they actually give the map a whole new dimension and almost a three-dimensional view. Let me show you what I mean. Now this line represents all the points on the ground at the same elevation above sea level. And you can see here how the lines follow that shape. Each successive contour line represents a change in vertical elevation above sea level, and this is called the contour interval, which is a set amount that is specified on the map. So let's say the contour interval is 10 metres. That means from the point on the ground, the next contour line is 10 metres above that. Now individually, that doesn't tell you anything. It's when you put all of those lines together that it really tells the story. You see, this is the picture that is shown. As you go up a hill or a mountain, the lines of the same elevation show you the steepness of the terrain. If the incline is steep, contour lines look closer together on the map because there is less lateral distance between the 10-metre change in elevation. Conversely, if they are further apart, then the terrain is less steep. So you see here that this section is extremely steep, whereas these are relatively gentle slopes. So if you're four-wheel driving or walking, you can use this information to choose the best path for you to take. Once you've got a bit of practice, your mind's eye will actually picture the map in 3D. And this is the real benefit of knowing what these contour lines mean.
Contour lines are imaginary lines that connect points with the same elevation. Each contour line represents one elevation. So here we have 700, 800. Contour lines never cross. Differences in elevation are shown with the spacing between contour lines. This is called a contour interval. Closely spaced contours represent steep slopes. So your contours here are really, really close together, and they represent a steep slope. Widely spaced contour lines, where you have a lot of space between one contour line to the next, represents a gentle slope. When contour lines cross a stream or a river, the lines bend to form a V shape. So here you have your contour lines and they're bending to form that V shape. That represents a stream or a river. The V points uphill. So the tip of the V points opposite the direction of the stream or river is flowing. Let's recap. What is a contour map?
Hey there. So the goal of today's video is to better understand what exactly a topographic map is, including what it shows and how to use the different features on the map to help better visualize the area that you're looking at. So let's jump right in. The first question we want to answer is, what exactly is a topographic map? Well, a topographic map, it represents a region, and it shows all of the geographical features of that region, including three-dimensional features like hills and valleys. The ultimate goal of a topographic map is to display these three-dimensional features with ups and downs and cliffs and slopes, rivers and streams, all of these three-dimensional features, but on a flat two-dimensional map. So let's take a look at an example. Here you can see a simple topographic map, often called a contour map. And the feature that should jump out to you on this map are all of these dark squiggly lines all over the place. Those lines end up being the key to topographic maps. They're called contour lines. So, what exactly is a contour line? Well, those contour lines that you saw running all over the map, those show the shape of the land, and they do it by connecting points that have equal elevation. Let me give you an example. Here's that map again. So if I look at point Y on the map, I know its elevation is 500 meters, and I know that because point Y is located directly on the 500-meter contour line. And so by understanding contour lines, I know that any point on that line is going to have that same elevation. Of course, the other lines represent different elevations, and we'll look at that in a moment. So let's take a closer look. One of the things you might notice is that some of these contour lines, not all of them, but some of them are labeled. For example, the 500 line is labeled, the 600 line is labeled, and these labeled lines have a name. Those are called index contours. And these are contour lines that are clearly labeled with their elevations. Now, unfortunately, on most topographic maps, there's just not enough room to label the elevation of every single line. And this is why we use index contours, maybe every second line, or every fifth line, or every 10th line, depending on the map. Either way, oftentimes you will be given what's called the contour interval. And the interval tells you explicitly the amount of elevation increasing or decreasing with each line. Now, this map is clearly labeled with an interval of 50 meters. And what that means is that as you go from one contour line to the next, there's going to be a change in elevation of 50 meters. So that contour interval tells you the elevation change from one line to the next. Fortunately, even if you're not given the contour interval, you can usually figure out what it is by examining the lines, and we'll see an example of that in a moment. Let's look at some other map features. Most maps are going to include a map scale, and this lets you determine the real-world distances between points as represented on the map. So for example, let's say I want to know how far apart points Y and Z were in the real world. I could use this map scale to figure out how many kilometers apart they are. A future video will take a look at how exactly we use a map scale. Finally, we'll notice that we also have a compass rose, and this is going to tell you the directions on the map and how they correspond with real-world north, south, east, and west. This allows you to orient yourself when using a topographic map. So that's a basic overview of how a topographic map works. Let's take one other look at a different example. So here's another one. You'll notice we have the map scale at the bottom, and we have the compass rose down on the right-hand side. We have a bunch of contour lines, and I also see the ocean and some streams and brooks flowing across the surface. We also see a bunch of different points that might represent landmarks or trailheads, anything like that. The one thing I don't notice is there is no labeled contour interval. They're not telling me how much each line is going up or down by. But fortunately, with a little bit of work, I can figure out exactly what the interval is. And that's something that's important to be able to do, especially when we get into more complex tasks like calculating the gradient. So if I zoom into the side of the map here, what I notice is that I do have two labeled index contours. I have the 250 line and the 500 line. And so I want to look at how many lines go in between them. In essence, I want to see how many jumps there are between these two index contours. So I can count them out. Here's 1, 2, 3, 4, and 5. So there are 5 jumps between the two index contours. Now let's do a little bit of simple math. So my change in elevation here is equal to 500 minus 250. Because I know that when I'm walking from one index contour to the next here, I'm going from 500 down to 250, or 250 up to 500. So I know that that difference is 250. So between these two lines, the elevation changes by 250. Now I also know that there have been 5 contour lines here. There are 5 contour lines difference between them. And so if I divide that 250 change in elevation by the 5 contour lines, I get 50 per contour line. And so that means that my contour interval on this map is 50. Now you'll notice I'm not saying 50 feet, 50 meters, and that's because I have no way of knowing. This map is not labeled to tell me what the elevations are measured in. So I'm just going to say 50, or I could say 50 units. So now I know that each line changes in elevation by 50 units. So there's a quick overview of topographic maps. In our next video, we're going to take a look at how we actually draw these contour lines on a blank map. If you like what you're seeing, please remember to subscribe.
Okay, and I hope that was helpful.